Hi everyone, this is page 14 of our video packet, and this is video 4-7 for Thursday, December 8th, and the homework that corresponds to it is page 12, number 1, so just one example. So this topic is finding absolute extrema with what's called the candidates test, and absolute extrema is different than local extrema. Local extrema are just like the highest or lowest point within like an interval, and absolute extrema are the highest and lowest points overall. So here's just some pictures that I might refer to later, but let's flip to the back. Okay. So yeah, and all of this stuff I got off of a website, which I'm citing up here. So absolute extrema refers to the maximum and minimum values of a function in a specific interval, and the interval has to be a closed interval. And there's this thing called the extreme value theorem that we're going to be using today. And this is called an existence theorem because it asserts the existence of a maximum and a minimum under an absolute maximum and minimum if there are certain conditions. So if f is continuous on a closed interval AB, then f attains both a maximum and minimum value there. So the two conditions are that the function has to be continuous on a closed interval. It doesn't have to be continuous overall, but it has to be continuous on this closed interval. And if it is, then it attains both a highest and a lowest y value overall. So the procedure that we're going to follow is right here. So you could read this if you'd like to. And we're going to do 3 examples. So the first example is a graphical one. So use the graph of f of x to state the following: absolute maximum and absolute minimum values. Okay, so to make this go smoother, what I'd like you to do is number the numbers on the axes. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. That's just going to be easier to see what points are what. And then what you want to do is you want to put a point on the endpoints of the function, but also on all of the local extrema. So like down here, you'd have a relative, a relative or a local minimum. Relative and local mean the same thing. Okay, and then up here in this neighborhood, you have a local maximum. And then this neighborhood, we've got a local minimum. And then this neighborhood, we've got a local maximum. And guys, when you're finding the critical numbers for a function, you see where its derivative is 0 or undefined, because look at all of these local extrema. This here, the derivative is 0. The tangent line is horizontal. Here the derivative is 0. Here the derivative is 0. Here's a sharp corner, so the derivative is undefined. So that's why you find where f prime is 0 or undefined, because those the x values there correspond to the local extrema of the original graph. Okay, so absolute maximums and minimums. So highest or lowest overall, I see that this point here is the highest overall, and by overall I mean including the endpoints. So you compare all of the local extrema to the endpoints. So absolute max, so I'll say abs max is f of 4, which equals 4. And then the lowest point overall would be this endpoint here. So absolute min f of 7 equals 0. Now the local maximum and minimum values, those would be the ones that I put the little parentheses around, because those are just the highest and lowest values within a neighborhood around it. So I'll say, okay, so local maxes I'll put here. So we've got f of 4 equals 4. That was also the absolute maximum. And f of 6 equals 3. And then local mins f of 2 equals 1, and f of 5 equals 2. Okay, so now number 2. Find the maximum and minimum values of this function in this interval. Okay, if they're asking for max and min on an interval, they're asking for absolute max and min. Okay, so max and min on a closed interval is the same as, so maybe we should write there, since negative 4, 2 is a closed interval. Closed interval means including the endpoints. Okay, this down here would be an open interval because it's not including the endpoints. Since this is a closed interval, they mean absolute max min. Okay, so we're going to do this on the back. And I'm going to add a little bit to the directions because I learned over the summer that they're going to want you to explain a lot of things using, like citing particular theorems. There will be, I think, four in total. So we have so far the intermediate value theorem, which I'm going to come back to, so we'll get more practice with that. This is the extreme value theorem. We need to be able to use these theorems in an explanation. So I'm going to show you how while finding the absolute extrema of this function on that interval. So the directions I'm adding is this. Before finding the absolute extrema, use the extreme value theorem. That's what EVT stands for. Use the extreme value theorem to justify their existence. So before even finding the absolute max and min, the extreme value theorem asserts their existence. So you can prove that they exist without finding them. All right, and sometimes you might want to do that, like if you're in the middle of an application problem and you're trying to, convince your reader that these things exist without actually finding them. That could happen. Alrighty, so it's going to go like this. All right, so first I'm going to prove to my reader that the absolute max and min actually exist, and then I will find them. So this is how you prove it. So let's just go existence proof, okay? And you don't have to write existence proof, but it might help you. So f of x is continuous on negative 4, 2, okay? That's a fact. This is a polynomial, and it's always continuous. It's continuous everywhere, so of course it's continuous on that closed interval. So f is continuous on this closed interval. And guys, that's all you need. That's the hypothesis of the intermediate value theorem. So I can jump right to therefore. Therefore, by the, extreme value theorem. I might have said intermediate a moment ago. Therefore, by the extreme value theorem, what does it say? It says that f of x must attain an absolute max and min on negative 4, 2, that closed interval. So it proves the existence of an absolute max and an absolute min. Okay, so now that we know now that we've proved they exist, let's find them. So the way that you find absolute maxes and mins is with something called the candidate's test. And the way the candidate's test works is you find the critical numbers of f. So you take its derivative, okay, f prime of x equals 3x squared minus 6x minus 9. Because, so here we're going to find all of the potential locations of the local extrema. And then we're going to compare them with the outputs of the endpoints. All right, so I'm going to factor this. X squared minus 2x minus 3. X minus 3, x plus 1. Okay, so the critical numbers are x equals 3 and x equals negative 1. So those are the potential x values of local maxes and mins. All right. Normally you'd go to the number line test and do the sign test in F prime, but that's not how you find absolute extrema. The way you do it is this. So this is the first part of the candidate's test. The second part of the candidate's test is to line up the candidates for the x values of your absolute max and min, line them up in a table. So you're going to have the endpoints at the ends. So -4, because we've got to be on this interval. So I'm not going to bother with any potential values, any critical numbers outside of that interval. So -4 will come first. Then this critical number is inside of that interval. So I'll use -1 next, then 3 still in, no, actually that's not. So 3 is going to be left out because it's not in it's not in this closed interval. Okay, we're finding the absolute max and min on that interval. Then, if you have a calculator, what I would do from here, so you're trying to get the y coordinates of these. So you're going to plug them into the original function. And what I would do, I think really this is the fastest way to do it, is to just use the table feature. So I'm going to go to y equals, and I'm going to graph x, x squared. I'm graphing f of x, the original function. And I think the fastest way of getting these corresponding y values is to go to table set, put it on ask, go to table, and then you can just plug in the x coordinates and get out the y coordinates. So I plug in -4, I hit enter. So -72. And then I plug in -1, so I get 9, and then I plug in 2, and I get -18. Okay, so -72, 9. That was a lot shorter than, plugging these in the home screen. Okay, so I'm just looking at this table. The absolute max will be the highest y value. So absolute max is going to be f of -1, which is equal to 9. And the absolute min will be f of -4, which is -72. Okay, so that's the first example. Second example. Okay, find the maximum and minimum values of that function in this interval. Well, guys, right away, I notice that this is not a polynomial. This has a denominator. So this has some discontinuities. And if this function is not continuous on the closed interval, it's great that we have a closed interval, but if that function is not continuous on it, then the intermediate value theorem does not guarantee the existence of an absolute max and min. So what I'm going to do is I'm going to graph this on that interval. So I'm going to do some further investigation because I know the the extreme value theorem is not guaranteeing that I have an absolute max and min. Oopsie, I'm up in the exponent. So before I bother to try finding them, I'm going to investigate a little bit further. Now I want it to be on this closed interval, so I'm going to go to my window and I'll just do from -1 to 2. So I'm like zoomed in on the interval I care about. And you see the asymptote, this vertical asymptote at x equals 0. So these y values are shooting up on and on and on up to infinity, down to -infinity, so there is no max or absolute max or min. The values just keep getting more and more positive, more and more negative. So there's no absolute max or min. Oh, I should point out, it looks to me like there is a local one, like somewhere around here. But that would not be absolute because these y values are way lower. Okay, so I'm going to say no absolute extrema. All right. Oh, and then, okay, at the end, I'm going to come back to this. I forgot to talk about this. I'll do it real fast at the end. So there's no absolute extrema. Consider the closed interval. Would your result change? And the answer is, pause it if you want to think about it, but the answer is yes, because the part where this was undefined, or the discontinuity here was at x equals 0. X equals 0 is outside of that interval, and x equals 0 was the only value of discontinuity. So within this interval, this function is continuous. So on this interval, we could apply the extreme value theorem, and that's what we're going to do on the back page. All right, I'm going to try to keep this under 28 minutes. I'm almost done. Okay, so just write that down. We're going to follow the same directions. So I'm going to do a little existence proof for my reader here. I'm proving the existence of the absolute extreme using the extreme value theorem. So f of x is continuous on 0.5 to 2. All right, that's all that you need is continuity on the closed interval. Therefore, by the extreme value theorem, f of x, and you could say has, use your own words, but I'll say has an abs, max, and min on this interval. Okay, and now the candidates test. Go ahead of me, guys, if you've got this. So candidates test. Okay. So I'm going to find the critical numbers. So I take the derivative, 2x minus 2x to the negative 2. And I got to find where the derivative is 0 or undefined. So I'm going to rewrite this so that it's easier for me. Get common denominators. Okay, so if you have it as one fraction, it's easier to see the zeros and the undefined values. Okay, so off to the side, f prime of x equals 0 at x equals 1. And if you wanted to set that equal to 0 and get x by itself, that's what you'd get. And f prime of x undefined at x equals 0. Okay. Now I'm going to take the endpoints along with either of these candidates that are within the interval, and I'm going to test their y values. So this is the second part of the candidates test. First you find the critical numbers, and then you put them in a table with the endpoints. So a half, and then 1, and then 2. Notice we knew we had a problem at x equals 0 because of part A, but that's not within this interval, so we don't have to bother with it. So I already have it typed into y equals, yep, I already have that typed in. So I'll just go back to my table. It's set exactly how I want it. 0.5, 1, and 2. So 4.25, 3, and 5. So we've got an absolute max f of 2. F of 2 equals 5, which was an endpoint. Absolute min f of 1 equals 3, which was one of our critical numbers. Okay, so there's that. Now, almost done. This will take 2 seconds. The reason why the closed interval is so important is that on this closed interval, we had an absolute min, I believe, at an endpoint. Okay, so f of negative 4 was negative 72. That was an endpoint. If the interval's not closed, guys, then at the endpoints, the function just keeps getting lower and lower and lower, or higher and higher and higher. And I just want to show you what I mean. So you might assume, okay, if it's an open interval, it shouldn't make much of a difference. I'll still have, since when we included negative 4, the absolute min was there, the absolute min of here will just be really close to negative 4. But the problem with that is that, okay, so let me go back and the problem with that is you can always get closer and closer to negative 4. Okay, and if you feel like you get what I'm saying, feel free to stop the video, but I'm just going to do a little demo if you don't know what I'm talking about. Okay, this is like a throwback to the beginning of the year. Okay, so here's the function, and suppose I'm a person who thinks that, I'm confused and I don't really see why this being a closed interval is necessary. So I have an open interval. So, and I'm assuming that since my absolute min was -4 when it was closed, my absolute min has just got to be like really super close to -4, or the absolute min would be at there. So I go to my table and I say, okay, so maybe it's at 3.9, the absolute min. So negative 17.41, but I can get, I need negative 3.9. Okay, that's a pretty low number, but I can get even closer, and I can get even closer. So there's no limit to there's no stop to how close you can get to -4. So there is no absolute min. It just keeps getting lower and lower and lower. So that's why the closed interval is important. And so yeah, the homework is just page 12, number 1, and I will see you tomorrow. Bye-bye.